Let's go ahead and get started. I was anticipating fewer students today than Tuesday, but much fewer. No, actually. A week from today, I hope that no one shows up here. There will not be any formal lecture. What I'm planning to do, though, is give you something that will induce sleep and provide you with a videotaped lecture. So you'll need to make sure and really get your caffeine level up before you start watching that video, but it will be on the D2L website. That will replace Thursday's in-class session. Being returned are homeworks 1 and 2. I apologize for those not getting back before the exam, but you might plan on something similar to that before exams 2 and 3 also, is not getting them back. But you do have access and availability to the worked solutions, and I hope that's some consolation to getting ready or prepared for the exams.
Are the grades going to be posted online?
I don't know if the grades will be posted. The question was, will the grades be posted online? That would be ideal. I haven't even gotten your things entered into D2L yet, but we'll see how that goes. Obviously, the grades or the exams need to be graded before that happens, and hopefully that will happen in the next few days, and we'll return those on Tuesday is the plan for exam 1. Today what I want to do is actually move all the way through chapter 3 and begin chapter 4 if we can. Chapter 3 will be addressed in homework assignment number 3. I think the date on that online is a week from Thursday, but I thought that would really be confusing to try to have you turn that in, so just we'll delay that being turned in until a week from Tuesday. That's homework number 3. Homework number 4 I will probably make on Tuesday, and it will be due roughly, I think, a week after the 30th of September, whenever that is, which might be the 6th of October, if I'm remembering my calendar correctly. And we may have homework 5 also due before the second exam, meaning you're going to have chapters 3, 4, and 5 as the plan for material content for exam number 2. And that will be inductors and capacitors, their properties, that's chapter 3. Treating those in circuits, transients, that's differential equations, that's chapter 4. In chapter 5, we'll begin doing sinusoidal steady-state analysis, which is doing circuit analysis just now with different kinds of sources than the DC that we've been thinking about. Now we'll be exciting our source or our circuits with time-varying waveforms, and in particular, those time-varying waveforms will be sinusoidal.
What chapters are we going through in this class? What is your 6?
To go through this class, I don't have the textbook with me. That should be on the syllabus. The question was, which chapters are we covering in this class? Not quite the entire book, but close. It's not just chapter 6. So we will go through, I can't remember. But we will get into transistors, which might be chapters 14 and 15. We'll get more material, obviously, than the chapters up through chapter or exam number 2. That's as far as I'm thinking right now, which is chapters 3, 4, and 5, content-wise. Today what I want to do is finish up chapter 3, which is inductor properties, which we just started last time. How we combine inductors. Those combine just like resistors. They add in series, and their reciprocals add to get the reciprocal equivalent in parallel. That's what I mean by like resistors. Then we'll finish chapter 3 talking about mutual inductance, and hopefully that will make sense. But essentially we will have two coils, and they'll be close enough together that they will start interacting. and because of their interaction, one current in one coil will induce a voltage in the other coil. So they have mutual coupling. That's where the mutual inductance comes into play. Hopefully we'll get into transients, which will then reinforce all of your differential equations material that you are presently taking or have already taken, depending on your passage through the curriculum. Here's the inductor that we had introduced last time. There's wire. It forms a coil around a coil form. And that current in the coil allows you to store energy in a magnetic field. And that stored energy gives us more interesting circuit behavior. We can now energize a coil and de-energize it to allow us to fluctuate current and voltage in a circuit to provide better or more interesting circuit analysis relationships. Eli is our friend. He's teamed up with ICE. But now for an inductor we want Eli. What was that trying to provide us as a mnemonic way of remembering what the current voltage relationship on an inductor is? That says that the voltage dropped across an inductor is proportional to the time rate of change of the current flowing in that inductor. Schematically, we still have this passive sign convention. Where this voltage-current relationship is written consistent with this schematic picture of the current voltage on an inductor. The inductor is given an inductance value of L, and the voltage dropped across that inductor is proportional to the time rate of change of that current flowing through the inductor. We started or just stopped with making some observations. Let's finish those observations for the inductor. And a lot of these can be thought through or determined just from Eli. V is equal to L di dt. The first one we already mentioned, but let's just redo it for completeness. The first one said that the inductor voltage and now when I speak of the current, maybe I should have said the inductor current. So this current voltage relationship allows us to conclude that the inductor voltage is blank when the inductor current is constant. If we have constant inductor current and V is equal to L di dt, you already have matriculated through and you're up to at least differential equations. Hopefully you now can answer that or fill in the blank. You now know from calculus, and I think that's in your first semester calculus, that the derivative of a constant is 0, and that's what I'm wanting you to use to fill in that blank. If there's a constant current flowing in that inductor, you do not have a voltage drop across that inductor. It looks like a short circuit, which is what the second observation explicitly says. It says an inductor acts as a short circuit to a constant or DC current. Another property is, and we've been talking about this already, so we're just listing these so that you have those in a list. The inductor energy is stored where is the inductor energy stored? It's stored in a field, not the football field or the softball field or the corn field. I saw some of you with John Deere caps from career day. Those were by your feet during the exam. So maybe you're thinking about working in a cornfield. Sorry. Making the equipment to put things in that field. Inductor energy is stored in magnetic field. Four, looking at that differential relationship between current and voltage, we can also say something about the inductor current and how it can or cannot change. Because the inductor current is differentiated in that V is equal to L di dt, that current cannot change instantaneously. That would give us nonsense in terms of a result of differentiating something that changes instantaneously. Then our delta T would be nothing, and we would be dividing by nothing, and that makes everything blow up. Meaning the inductor current cannot change instantaneously. Because of that, an inductor actually opposes changes in current. It's hard to change the current in an inductor, so it likes to keep doing what it's doing. You can't be changing, or it opposes or sort of impedes rapid changes in the current. And consequently, sudden changes in the inductor current, not instantaneous but sudden changes in the inductor current induce very large or large voltages across the inductor. We have the differential relationship on our inductor, which says that V sub L of t is L di sub L dt, and we can now solve that for the current in terms of the voltage. Or if we rewrite this and solve for di sub L, we're looking at this integral from, let's say, t naught to t1, di sub L is equal to 1 over L. We're assuming L is now constant, and we can factor down to the integral. The integral from t naught to t1 of V sub L of sigma d sigma. I think we didn't like tau as our dummy variable of integration, so we're going to use sigma. With that relationship, we can solve the left-hand side and say, well, the inductor current at the upper limit of integration, I sub L of t sub 1, is going to equal this integral of inductor voltage from t0 to t1 plus whatever we started that inductor current at the initial time, I sub L of t sub 0. A lot of times we may assume the inductor current is 0, then we get I is equal to 1 over L integral of V dt. Let's derive, similarly to what we did with the capacitor, let's look at these power and energy formulas. for the inductor, which will be dual relationships to what we found in the capacitor. The dual does not mean the same. The question was, does dual mean the same? It just means, dual means that current and voltage basically sort of flip places in this case. So what was true for voltage in the capacitor is now more like what's true for current in the inductor, and I think you'll see that in these relationships. The power is, formula-wise, is the same. Instantaneous power on our inductor, if I just said what is that in terms of current and voltage, what would you tell me? It's the product of those two, correct? That's just the voltage of the inductor times the current of the inductor. So those are L's. But the voltage across that inductor, according to Eli, is L di dt. And if we needed the power and all we had was current, then we could look at the derivative of the current, multiply that times the current, and scale it by this proportionality constant, which is our inductor, and we have the instantaneous power if we did not have the voltage measured across that inductor. We can now find the energy in that inductor, which is this integral of power. And if we plug in what we just wrote down above, we have this L, di sub L, let's say sigma, d sigma, I sub L of sigma, d sigma. And that's now this, the L can come out front, and we have basically x dx integrated, and that gives us 1/2 x squared. And let's just throw away or say that the initial current was 0, and that allows us then to conclude that the energy in the inductor is 1/2 L I sub L of T in joules. Thank you. I sub L squared. Meaning the energy in this inductor is proportional to the square of the current through that inductor. And what was the energy in a capacitor proportional to? The voltage squared. That's this dual relationship between the capacitor and the inductor. Let's quickly go through this idea of combining. I always debate whether to do this because you can figure it out on your own. But it's one way to remind ourselves of the relationship between current and voltage of inductors. If we have a series combination of inductors, we could write that schematically or sketch a picture of what that looks like. Here's, let's say, L1, L2, and L3. Let's define these voltages around that mesh. consistent with this current I that's flowing through, and since it's a series network, the same current is going through not only the source, but also all three of those inductors. We can now, just like we've done before, KVL and KCL still hold. That's why we really wanted to learn those for the inductors. Now we can rely on those to analyze this circuit. If we start down at the lower left-hand corner, we have minus V sub S plus V1 plus V sub 2 plus V sub 3 all equal to 0. And that shouldn't surprise anyone, that relationship. What we want to do is replace the inductor voltages with their expressions in terms of current. And in this case, the current's the same in all three. The voltages may not be the same. Just like if we had a series combination of resistors, the current going through those resistors is the same, but the voltage dropped across each individual resistor may not be the same. Likewise here. But we do know that they're all proportional to the time rate of change of the current flowing through those inductors. Meaning, we now can say that V sub S of t is equal to V1, which is L1 di dt, plus V2, which is L sub 2 di dt, plus L sub 3 di dt. Remembering that the current is this series current. It's the same through all of those elements. The time rate of change is consistent with all three. We can factor that out if we wanted to. And now somebody could say, you know what? I can just model those three inductors, if need be, as just one new inductor that's the sum of the three individual inductors. Or inductors in series add. L equivalent is the sum of those three inductors. And we can do the same thing for the parallel combination of inductors. And you can probably have a little bit more fun. Now you get to draw more things, right? You like to draw. Now you get to draw these curly things. Those aren't supposed to look like resistors. These are supposed to look curly. Mine may not. Now I'm getting hungry. I'm thinking curly fries or something. Sorry, I shouldn't have said anything about curly. Beef jerky. No, I might get choked and then we wouldn't. Oh, now you'll really want to feed me, right? Oh, maybe we can kill this guy off. Not a bad idea. All right. Probably is what you're thinking after that exam, right? Here's a current coming in. This is all at the same node. All of those inductors, which allows us to think about the voltage dropped across all of those inductors being the same. They're in parallel. They share those top and bottom nodes. But we know these currents are different because the inductors are not necessarily equal in value, in their inductance. Now we can apply KCL to that top node, which says, and that still holds, just like KVL holds, the current coming in equals the current coming out. which for this particular demonstration, we want to write the current through those individual inductors in terms of the voltage. The voltages are the same, so we're going to try to factor that resulting expression out of this equation. Do you remember what the current, well, here we had Eli, which says V is equal to L di dt. If we turn that around, I is this 1 over L integral of V. If I'm doing my math properly, and I'm doing it with an indefinite integral, just to be as clean as possible or as easy as possible, I could say, well, this particular current then, I sub 1, is 1 over L1 integral, let's just go from a lower limit to an upper limit, of that voltage is the voltage across that inductor, d sigma, plus 1 over L sub 2, integral from 0 to t of V d sigma, plus 1 over L sub 3, integral from 0 to t V d sigma. That integral of the voltage is consistent on all of those. We can factor it out. And somebody could say, you know what? I want just to think of that as one common inductor. And now we need to combine those in this new relationship, which says that inductors in parallel, you can take the inverse of the sum of their reciprocals. Where this formula is for 3 inductors in parallel. Questions on that? That's how we can combine inductors. I'm sorry? Oh, that's sigma. That's a sigma. So I went now up here in this voltage expression. Voltage is a function of time. And so now I didn't explicitly show the argument on my voltage earlier. I didn't want to get writer's cramp, and so I left it off. Okay. But it's really there. It didn't just magically show up halfway down. It did physically, but in reality it was always there. Question?
In the last 2 lines, the L equivalent, those aren't the same L equivalent.
Where did I mess up?
1 over L equivalent. Those 2 L equivalents aren't the same. Are they?
So now what I've done is I've set 1 over L equivalent equal to this sum of 1 over L's. So now if I take the inverse of both sides, I'm going to get L equivalent is 1 over the sum of those. Is that not correct? Or is that not the question? What? So the question, I think, was, is the bottom boxed answer the same as equating those 2 coefficients in the 2 lines above that? And my answer is, I hope so. It's supposed to be. So if we take the inverse of both of those, you will find that L equivalent is 1 over the sum of the inverses, which on a calculator it may be easier to just take the inverse and sum those inverses and then take the reciprocal of those inverses. But if you just have 2 inductors in parallel, you can do that relationship that we've done before, the product of those 2 over the sum of the 2, if you have inductors in parallel. Other questions on combining inductors? Let's then move into the last part of chapter 3. Which concerns mutual inductance. For this, we're going to actually have two different coils. And I'll draw that schematic in just a minute. But two coils can be arranged to allow mutual coupling of voltages among the coils. So now you thought you were having fun sketching before. Now watch this one. Oh, that's almost pretty. No, it's not. You can do better than that. So make your coils consistent. Mine don't look very consistent. Now I have to do just the opposite. Now I have to come from the right side. And those don't have to be the same number of coils or the number of turns. One can be different than the other. Now if you have your infamous nail that you're winding coils around, if you're creating an inductor or a transformer, now that's probably not the case, but in the old days when you had some way of converting between AC and DC, you probably had a wall wart that probably had a transformer in it. It now has two sets of coils in it, and they're coupled. But here, can you tell I'm covering up the right coil? Doesn't work anymore. I guess I need the Elmo. And I can't do, I'm not quite wide enough to do that or tall enough, but use your imagination. If you covered up the right-hand coil, you would just have one inductor, wouldn't you? So we would label that L1. Likewise, if you covered up the left coil, you would just have an inductor L sub 2. And with those, you could say, oh, I have a V1 and I have a V sub 2. And maybe with this one, I'm going to say here's I1 and here's I sub 2. But because of the way these are built or configured, and I'm going to refer to this as figure 1, these two coils, if you now had your nail and you put two coils, one here and one there, you could actually maybe imagine the fact that if I put current through this top one, some of that flux would actually link to this second one even without current flowing, and it might establish a voltage in that bottom winding. That's what's happening here with these two. And this is now going to establish a mutual inductance between that, and that mutual inductance, or the voltage V1, is not only going to be caused by the current I1, but it's also going to be caused by the current I sub 2 that's flowing. Now, there's one more piece of information that you have to keep track of because of that mutual coupling or that mutual inductance, and that is how these coils are physically wound. And the notation that we use schematically is to put dots on these coils. And the location of those dots and how those currents enter those dots or leave those dots is critical for how the M is applied in your mutual inductance formulas. Let's just now say that right now we have self-inductance or since we have two self-inductances, L1 and L sub 2. That we're comfortable with. Now we're introducing this new piece, which is called the mutual inductance. And that's N. Now let's see if we can talk about these dots and currents and how we're going to express this. Hopefully I've convinced you that current flowing in I1 and I2 will both contribute to the voltage V1 and V2. Now we just have to figure out how that works. And the way that we figure out how that works in terms of M, if I said, okay, what's Eli for L1? You would say, oh, that's V1 is equal to L1 dI1 dt, right? But now we have an induced voltage because of that mutual coupling, and because of that, V1 can actually have a piece due to I sub 2. And so that additional piece is going to be M dI sub 2 dt, making up V1. The key piece that we have to worry about is the sign on that M. And now that's why I'm trying to make a big deal about the currents and these dots. In this particular figure, the currents are in what may be referred to as N to the dot. What in the world? It's always into the dot. Okay, so I1 is going into the dot before it goes through the coil. Similarly to how we did the sign convention and the positive and negative signs. On the left, I1 is going into the dot before it goes through the coil. So that's what we call into the dot. I2, what's that doing? Is it going in or out of the dot? In. If I2 is on the lower branch, then we would say that I2 is flowing out of the dot. Is that making sense? If the current goes through the dot before it goes through the coil, that's what we call in. Now, if both currents go into the dot, or if both currents go out of the dot, the sign on M is positive when we put it into our formula. That's what I want to try to make clear. Let's write that down. If both currents enter, or both currents leave the dotted terminals, then the mutual inductance is positive, and I'll refer to that as aiding, or it aids, and that's what was shown in Figure 1. By that, here's the formulas that you can now write. We have V sub 1 of t is going to be related to the time rate of change of I sub 1 because of this self-inductance. It's also going to be a function of the current in the second winding, or its time rate of change, by the mutual inductance. And if we have these currents both entering the dot, then the sign on that is plus. Likewise, V sub 2 is M dI1 dt plus L sub 2 di sub 2 dt. And that's figure 1. That's what I mean by positive. This is positive, as is that is positive. Question?
Is there a reason why you put the M before the L in the second equation?
Is there a reason why I put the M before the L in the second equation?
Oh, I see. Never mind.
Just because I kind of like to do I1 then I2.
No, I didn't realize that I won.
So in the top one and in the bottom one, we both have I1 and I2. So if you were doing this in a matrix vector notation, your right-hand vector might be di1 dt over di2 dt, and then you would have this matrix of inductances. The diagonals would be the self-inductances, and the off-diagonals would be the mutual inductances. And in this case, your off-diagonal terms would be positive. It's not critical that you have those in that order. I just did it, and now I'm looking ahead at my notes, and the next one I didn't do that way. Maybe I'll do it, though, consistent, so you're not completely confused. Is it clear what I'm meaning by the sign and going into the dot? All right, so let's, pardon?
Is it a convention where the dots go instead of making all these tables?
It's not only a convention, but it's how they're manufactured. It's how they're built, actually. Somebody has to tell you where the dot is. Is the dot here or is the dot there? Because you need to know, is this mutual inductance aiding or opposing this voltage relationship that I'm looking into? Let's draw figure 2. So figure 2 is the following. Again, two coils that are close to each other. They each have this self-inductance. They both have a current flowing. And because of their close proximity, they have a mutual inductance relating or linking those coils. But in this case, for figure 2, I'm going to make it just a little different. Now I'm going to have I1 go into the dot, and I2 actually go out of the dot. Meaning, I2 goes through the coil before it touches the dot. And so it's going out of the dot is the convention that or the terminology that I'm using. The phrase then, or the sentence, is the following. If one current enters a dotted terminal, which in figure 2 is which current? I1 is the convention or consistent with this terminology of I1 enters the dot. If one current enters a dotted terminal and one current leaves, a dotted terminal, then this mutual inductance, or the mutual inductance, is negative. Or instead of aiding, it's now opposing or opposes. And that is what we were trying to illustrate with figure 2. And the expressions now, how do you want me to do it? Do you want my I's to go 1, 2? Or do you want my M's to be lined up on top, stacked on top of each other?
Same as before.
I's, same as before. The ayes have it, okay? Good. So what am I writing? I1, I2. They're derivatives, right? They're time rate of change because we want to know how are they influencing the voltages. We have V sub 1. That's going to have some voltage due to the self-inductance. That's L sub 1 di sub 1 dt. And it's going to have some voltage due to this coupled or mutual inductance. Except now, since one goes in and one goes out, there's our minus sign. V sub 2 of t has some self-inductance. As before, that current is flowing through the coil, and that establishes a voltage drop because of the time-varying nature of the current in that coil. But it also has some mutual inductance that's coupled into that, and now I need to make sure that that has a negative sign. Because one current went into the dot and the other one went out of the dot. And I think you can see that there are a lot of different ways that you can sketch that and have currents going in and out of the dot. Is that making any sense? Here, let me just play a little bit. Suppose we have this and I'm going to simply put some things down, and you're going to need to tell me whether it's going to be aiding. Question.
Is the dot just a reference point, or?
The dot is a reference point. You remember how you always in physics were going right-hand rule, left-hand rule? That's going to sort of influence how your coils are wrapped around this coil form. And so depending on how those wires are wrapped around that coil form is going to influence how those coils couple to each other. And if you wrap those and drive those in a certain way, it's going to determine whether that coupling is positive or negative, whether it aids or opposes. And because of that, we need to then show, for example, dots on that on that particular coupled set of coils. Here, let's say here's I1, and let's say this is I sub 2, and let me say that the dots are here and here. Well, the dots basically tell you how the coils are wrapped around the coil form. And the most important information really is how those dots are related to the currents that you're driving those coils with. We in this class will simply give you a schematic and say, here's I1, here's I2, and maybe here are the equations. Where do the dots go? Or here are the dots, what are our equations? Or here are some currents. You tell me what V's are for a particular sketch. And that sketch would then have the dots and the currents defined. So do you see how we could play this on the exams? A lot of different ways. Is this a positive, or we could say aiding or opposing set of currents and dots?
Aiding.
Aiding? Is that the consensus? Because the currents are all going into the dots, right? So that one, you're getting it, right? So if I went like this, that's opposing. Does everybody understand what I'm meaning by dots and aiding and opposing? Okay, you're going to ace all those problems on the exams and the final. Correct? Good. That's confidence. Did you have that confidence Tuesday? No. That's what I thought.